Greetings, and welcome to our Fall 2014 Fluid Mechanics presentation. We will do the following where we will simulate using a mathematical model in MATLAB to simulate the flow as seen in image 2, using the information given from image 1 or the problem 6.101 from the textbook. Now basically, as you see in image 3, you see a very simplified equation of what we use is called the Navier-Stokes equations, which is a set of very complex equations that will give you for our particular case, the behavior of a certain fluid when it flows through, in this particular case, two parallel plates. So why a mathematical model? Well, in this particular case, due to the complexity of the equation, mathematical models are useful in situations when you have many variables, and they can create digital images, or in this case, modeling, that will represent how a system or a process works, in this particular case, the fluid flow. And also, mathematical models are able to use mathematical language, again, image 3, to describe the behavior of a system. So with this, I'm going to go ahead and pass it on to my classmate so we can start to see how all this information is going to be input into MATLAB so we can create an app to simulate this flow as seen in image 2. Thank you for your time.
Hello, this is Rashid Hamzin. I'm going to talk to you about part of the flows project that the JEDI Council did. Initially, we used data that was given in the question, and we used the flow equation to get the equation for the fluid velocity with respect to y, which is the distance from bottom to the top plate. And with this equation, we put it into the script and got the exact same graph that we did as we did and when we solved it by hand. And what we did was we built an application that was able to take inputs as Ymax, which is the distance between two plates, and shows the velocity profile graph. And for the second version of the app, we put in a few other inputs, which was the velocity of the top plate, pressure gradient, and the initial inputs, and we got the same exact profile. And we also put in different fluids as seawater and water and glycerin to see how the flow velocity profile is going to be. For the final version, we also added in a table where you could see the different velocities at different distances between the two plates. So you can see how the velocity changes as you go from the bottom to the top plate. Thank you.
After we had the basic graph, we wanted to create an app. In order to create the app, we had to use the graphical user interface. The first step was to add axes in the graphical user interface. We wanted interaction between the user and the app in order for us to understand how changing the parameters and even the liquid would change the result of our graph. We added edit text boxes where the user would be able to enter a value, and that value would change the result that we would get on the graph. To convert the process we wanted into code, we placed the text box into the panel. We opened Property Inspector for the text box and changed the value in the string to the value that we wanted to show initially. We also changed the tag name to the name we wanted to use. We wanted to put a pop-up menu for the liquid values, and we wanted the program to be executed once the value from the pop-up menu had been chosen. So you will see in the editor that the bulk of the coding is under these lines of code right here. For our equation and plot to respond to the changes the user inputs into the text box, we use the codes right here. This code allowed us to use the input of the user as a variable called ymin that would affect the outcome of the graph. We used similar code for ymax, u, and pressure gradient, only having to change the name of the variable and add text boxes. Another feature that the team decided would be handy was the addition of a pop-up menu. The menu would allow us to see how changing the liquid would affect the graph. We chose 4 liquids to study. They were SAE30 oil, water, seawater, and glycerin. In order for our group to make the graph respond to our choice of liquid, we created a pop-up menu in the panel. Next, we went to the property inspector and changed the string into the list that we wanted. We changed the tag to pop-up choice, and using the code right here, we were able to assign a value to the variable mu based on our choice in the pop-up menu, since we used the equation right here. For our graph, any change in u, y, mu, and pressure gradient would affect the graph that the app would show us. After we were able to establish a graph, we used these equations to make modifications, such as modify the line of the graph, the title, the axes, and a moving plate at the top of the graph. When we use a table that was added with these lines of code right here, we are able to get values for the velocity at various points across the channel, and we are able to come up with the result right here.
The equation for fluid flow has been reduced from the Navier-Stokes equation similarly to laminar flow equation. This is due in part for the assumption of laminar flow for this particular problem. However, fluid flow differs from laminar flow in that one of the parallel plates is fixed and the other is moving with a constant velocity u in the x direction. Since there is no velocity in the y or z direction and flow is assumed to be at steady state, the v and w components in the y and z direction of the Navier-Stokes equations are equal to 0. Also, this local component U.T.T.E is assumed to be 0 as well. This is due to the assumption of steady state within the fluid flow. From this coordinate system here, in boundary conditions, we're able to use our MATLAB app to simulate a velocity profile for the various fluids. As indicated by the equation for fluid flow, the distance between the parallel plates b, the velocity of the moving plate u, the height y, and the pressure gradient seen here. A velocity profile for this particular fluid of SAE30 oil.
Mathematical simulation using software such as MATLAB serves to demonstrate how an otherwise abstract process, such as fluid flow, works in a more visually defined and clear way. For the project, a code was developed for MATLAB that made the simulation possible using the parameters set up in the problem. Through the application that was developed, the fluid flow that was presented in problem 6.101, in this case correct flow, was shown. The problem was initially solved using conventional means and through the calculation and simplification of the Navier-Stokes equations. Equation 6.140 was used to develop a general equation to define the velocity at various points across a channel and show the results on a plot. The results depended on several parameters: the space between the plates, the velocity of the upper plate, which moved in the positive x direction, the pressure gradient, the dynamic viscosity of SAE30 oil, and the assumption of laminar flow. The app in MATLAB was developed using the constraints specified in the problem, and it accurately illustrates correct flow for SAE30 oil, as well as 3 other fluids that were included for demonstration purposes, and which can be chosen here.